To understand how permutations work, to understand the centerpiece of this section, I have to introduce a different piece of notation here called a factorial. But to understand what a factorial is, I'd like to give an example first. So let's say that you go to a race, and there are 8 people in the race, and before the race starts, you want to pick a winner for obviously no reason except the fun of it, to make it more interesting, because gambling, as far as I know, still isn't legal in Florida or many other locations, so definitely nothing illegal going on there. You're just curious. But before you go there, if you want to pick the winner, or you want to try and pick everyone in the race, well, if you think about it, you have 8 options for whoever can win. Right? So you got 8 people there, any one of them that can win. Again, probably you've got a favorite, but any one, technically speaking, can win at the start of the race. So, got 8 options for whoever comes in first. And then from there, if you want to pick who could come in second, well, you've got 7 options. And by fundamental counting, if you want the total for first and second, that's 8 times 7. Where you only get 7 there because whoever came in first can't also come in second. That would both be incredibly unfair, incredibly unsporting, and probably would break some laws of physics unless they are very fast. So, got 7. Then if you want to get third, same idea. Can't have person who came in first or second also come in third. So you got 6 left, could be any of them. 6. Then from there, you would have 5, 4, 3, 2, and 1, all following that fundamental counting idea, which gives us a total here of 40,320 options for how the race could possibly go. Even though realistically you probably know, well, who's got the best chance. But in a lot of races, in particular, we don't actually care about all of the order unless you have a personal investment already in some of the people. You really care the most about the top 3, who gets the medals, as it were. Where for the top 3, all you have to think about is how many ways you can get the first, then second, then third. You don't care about those other 5 quite as much because there is no copper medal for 4th place, and there's certainly no tin medal for last place. You only get the top 3 that win anything in particular, although you might get other stuff in there for who gets what. But from there, you'd have 336 options because 8 times 7 times 6 is 336. Again, they're not all the same options, but we're being as general as possible here. We're giving as many opportunities as possible here because anyone who's in that race probably worked very hard to get there. Usually, people work very hard to get into foot races. But first thing we should notice here is that this kind of notation with all of the options written out, well, it's clunky. It's kind of long, it's kind of cumbersome. When I have that there with all 8 of those people, then all 7, then all 6, then all 5, then all 4, then all 3, then all 1, it took time just to write it out, much less actually compute it. And if I had any more than that, it would get worse and worse and worse and worse and worse. So, to help ourselves, to make ourselves a little bit more, let's say, streamlined, we could take a value like this, and instead of writing it in terms of that 8 times 7 times 6 times 4 times 3 times 2 times 1, we would write this as 8 with an exclamation point to say 8 factorial, where that exclamation point there does not indicate excitement at numbers, although hopefully all of you are excited with numbers. What that says is we're going to take the descending product of the natural numbers less than our value. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 and 2 and 1, where this sense of convenience is where factorials come from. We just like having something a little bit more condensed. I think I've said it before in this class that mathematicians, they tend to like abbreviations, so we like to invent them where we can have them, because writing out all of those things is a pain. And well, we do enough mental labor to try and avoid physical labor as well. And for here, what we can think about this more generally as trying to tell us is a total number of options where we care about order and do not have repeats. So we have some amount of things where what gets picked first makes a difference, what gets picked second makes a difference, what gets picked third, and so on, just like in this race here, because they care and you can't have repeats. That's how we end up with a factorial, where in particular, we have the value 0 factorial equals 1. And there's a notational reason for that we'll get into when we talk about permutations and combinations later, but there's also a counting argument you can make there, that if we're talking about the number of selections where we care about organization and can't have repeats, there's trivially only one way that you can pick nothing, and that's by, well, not picking anything. But that sort of thinking is a little bit more complex than it really needs for this class, so let's just take a bit more practice here with how this notation ends up working out. So for this, we want to compute the following expressions using factorials. In the first case, 7 factorial over 4 factorial. In the second, 59 factorial over 58 factorial. And these do look like they're going to be a real problem. And I'm going to show you that the nice thing about factorials is that they end up reducing into very nice things, or at the very least they work better than it might initially appear. In our first case, we're looking at that 7 factorial over 4 factorial. What happens here can be written out the long way as 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 4 times 3 times 2 times 1, which would end up being 50/40 over, what is that? I can't believe I know that one, but I forgot the second one. I have to double check it in my head, is 24. Or we could notice a little bit more cleverly that we've got 4s, 3s, 2s, and 1s, which means that the other way we could have done this is in terms of just 7 times 6 times 5. Because what always ends up happening when you have a factorial over a factorial is a lot of the terms cancel. And the reason why that goes that way is because when you take a factorial like 7 factorial, you can pull out a 6 factorial, or a 5 factorial, or most meaningfully here, a 4 factorial, and these will cancel, leaving us with 7 times 6 times 5, or, perhaps more usefully, 210. Meanwhile, for our second case, it's basically the same thing here. You see that 59 factorial over 58 factorial, and you think, oh god, I have to multiply out all 59 of these things and all 58 of these things. That's going to take a long time. My hand will hurt. That won't be very fun at all. Or, you could recognize here that you can just take out a 59, leave your 58 factorial to get killed by the other 58 factorial, and this just gives 59, in some sense, total options. That gives us our values there. And this leads us towards our important piece for this section, the permutations. But before I get to that, I want to leave one small bit here for calculator work, and one important piece here for the algebra of these things. Where for one, if you want to check your stuff with calculators, there's often nice functions, nice functionalities built in for handling all of the things we get in these sections. In particular, we have that nice little exclamation point that gives us factorials. But also, when we're dealing with these things, it's very, very important that you note these kinds of multiplications and divisions and handle them carefully. That if we have something like n times m factorial, this is in fact, and in all but really a few very special cases, going to be considerably smaller than n times m quantity factorial. Bringing in another term is very, very different than pulling together two terms and taking a factorial there. Something like 59 times 58 quantity factorial would be something in the vein of 3,000 factorial, whereas this is only 58 factorial times 59, which, again, it's weird to think of that in terms of only, but that's the way this ends up going. And that largeness that we're not quite seeing here, because I was careful in setting up these values, is actually incredibly important, as it's the basis of modern data security. That the reason why computer transactions by credit card are safe isn't because they're so perfectly encrypted, it's because trying to guess a credit card number isn't the sort of thing a computer can do reasonably quickly. That's why if people want to hack you, they're going to phish. They're not going to just use these numbers. It would take too long. So they don't, and that's the entire reason why it works. And figuring out whether or not that is actually certainly always the case, that you can't use something a computer's good at, like a polynomial, to approximate a thing like this that doesn't appear polynomial, is one of the biggest problems in computer science, discrete math, and a whole bunch of other sub-related fields, but it's outside the scope of this class. So, for now, let's actually get into that big notation that we're going to be introducing, permutations.